So yes, I think it's time. So, hello everyone, I'm Mohit Shenvi, and welcome to the 2021 ISTVS Digital Event Series consisting of student research seminars and Terra Mechanics Bytes. So, today is a student research seminar which will be presented by Ms. Hannah Lyness, who is a PhD student at the Robotics Institute at Carnegie Mellon University. Her topic of her presentation is quantifying reconfigurability for small unmanned ground vehicles. Ms. Lynch is also the recipient of the inaugural Nevada Automotive Testing Center Travel Award that was created for a student to have a scholarship to go to the ISTVS conference in Prague back in 2019. So we hope she had a very nice time when she was in Prague, and I hand over the rights to her to tell us more through her presentation.
Awesome. Thanks, Mohit. All right, am I coming through all good? You can hear me and see my presentation?
Yes.
Awesome, perfect. Well, thanks for that introduction, Mohit, and thanks everyone for joining. I know that this is a busy time of the year trying to finish up things before the calendar year ends, and for some of you, this is probably the middle of the night, so I appreciate everyone joining. This presentation, I'm hoping to get a little bit of practice speaking about the work I have done and the work that I'm planning to do. In addition, I'm hoping to get some feedback, especially because I know a lot of us come from a different lens than perhaps I'm coming from. So I'm really anxious to hear what everyone has to say, and I think it'll be pretty valuable feedback. So as Mohit said, I'm a student at Carnegie Mellon. My advisor is Dimi Apostolopoulos, and today I'm going to be talking about some of my thesis work, which is quantifying reconfigurability, mobility, and complexity for small, tracked, unmanned ground vehicles. So to start off with, robotics, as we all know, have been used in increasingly complicated and unstructured environments. For example, we've seen robots being deployed in disaster sites, helping out with urban search and rescue. In addition, we've seen unmanned vehicles used in agricultural fields. In addition, robots have been deployed in places as crazy as volcanoes. We've seen robots used in mining and industrial applications, in battlefields, and even in cities. For each of these applications, we see a wide variety of platforms for these ground vehicles. For example, in disaster sites, we've seen snake-style robots that are able to squeeze into very small confined spaces. A four-wheeled wheeled vehicle is a very common platform for a variety of different applications, shown here in the agricultural example. And legged vehicles can offer great advantages for moving over different obstacles and having high ground pressure, as in the case of this vehicle that needs to go down very steep slopes. Six-wheeled vehicles with high suspension can offer great ground contact, even going over rough terrain. And tracked vehicles can provide a great deal of traction in especially slick environments or environments with very loose terrain. And in this example here, we've seen the short vehicle with the 6 wheels that's able to maneuver in and out of people, as in the case that you would need in cities. So even within a single mission, for example, the DARPA Subterranean Challenge, we've seen a wide variety of different styles of ground robots. For example, the 4-wheeled robot, the tracked robot, a somewhat reconfigurable 4-tracked robot, and the walking robot. And each of these vehicles has their pros and cons. For example, a 4-wheeled vehicle is a very common application. There's a lot of research before. A lot of control algorithms have already been developed for this type of vehicle. For example, the legged vehicle can go over very high point obstacles. However, we saw in the Subterranean Challenge, it struggles on icy or muddy terrain where the legs aren't able to get traction as well. So the main idea of my research is that mobility systems could be combined in a reconfigurable way to allow the robot to have advantages of both systems. Reconfigurability isn't a new idea. Beginning in the late 80s, we've seen researchers explore ideas of reconfigurability for robotics. So Fukuda and Nakagawa are widely regarded as the inventors of this idea of creating multiple smaller robots that can be combined depending on what the mission would entail. In this same year, we saw Kanade et al. Working on a reconfigurable manipulator, and manipulators that are able to grasp a variety of different things have been a great application for a reconfigurable or modular system. In terms of mobility systems, we've seen, we may be familiar with PackBot or iRobot or Endeavor's ground vehicles, where they have 2 front paddles that can enable the robot to have a larger track length and can also be used to help distribute the weight differently depending on if you're going over gaps or across stairs or things like that. In addition, a couple years ago, we saw some researchers capitalize on this idea of an origami wheel to be able to change the diameter and width of a wheel using additional actuators in the wheel. And just as early as last year, we saw a pretty whimsical example of reconfigurability in robotics. A team over at MIT developed a series of similar cores that could move into different shells. And these shells could offer different applications, for example, spinning this arrow or moving a platform up and down, all with a consistent center core that could be used in a variety of different manners. So modularity and reconfigurability can offer benefits to a vehicle, for example, portability. By taking off different aspects of the vehicle, it can make it easier to store or easier to transport. This can also offer the vehicle flexibility. For example, Boston Dynamics Spot has a variety of different sensor payloads that can be added on top of it, depending on the environment that you're in and what you might need to sense. In addition, modularity and reconfigurability can offer advantages for maintenance. Using these industrial robots as an example, they all have a common central base, and this makes it easy for production and also maintenance. You don't need specialized tools or parts for each robot, and then they have specialized top portions that can be adapted for each of their separate purposes. I'm mostly interested in the reconfigurability of the mobility elements. So for example, in the image on the left, we've seen a walking robot that can then kneel down on its knees, which have wheels on it, that can offer the robot additional stability when it needs additional force parallel to the ground. I've mentioned before the iRobot idea of using these front paddles, and you can change your weight distribution and even use them as a very basic manipulator. And in the image on the right, we've seen an example of a vehicle that has wheels that can reconfigure into these four-pronged devices that can help it go upstairs. So we can offer additional terrain that we might not have been able to visit otherwise with this reconfigurable element. The slice of robotics that I'm most interested in is ground vehicles under 50 kilograms. This is a more accessible weight range for me as a researcher. In addition, this weight range for tracked vehicles is understudied compared to large wheeled vehicles. I won't go through all of these examples. I'm sure most of us are familiar with Becker-Wong, but most of their equations were developed for larger vehicles that we might see in a military or industrial setting. And there's a caveat on many of them that say, only intended for vehicles over a certain weight. On the other side of things, researchers like Marion Griffith have worked to develop these equations for lighter vehicles, but primarily focused on wheeled vehicles. So we're interested in smaller tracked vehicles, and that's what the majority of my research application is. So my thesis question is, how can mobility system reconfigurability be quantified to inform small unmanned vehicle design to optimize mobility performance over a variety of terrain? I'll stop here to make sure I'm not missing any questions in the chat. I don't see any. Awesome. All right, I'm going to press on. Feel free to ask questions as I go, or I'll have plenty of time at the end for questions. So the approach that I'm taking with my work is to first start off by defining the workspace. I looked at a variety of different resources to try and make sure that I understood the definitions properly, and then make sure that I'm incorporating all of these different lenses in different applications that reconfigurability could be used in. After that, I sought to create quantifiable metrics. And for these metrics, I chose to define mobility, trying to see how good this vehicle can move over a variety of different terrain, complexity, which is something we want to minimize in our vehicle, and reconfigurability, which I chose to select elements that would be a cost to our vehicle that would not otherwise be there without that reconfigurable element. After this, we designed and created a manually reconfigurable robot that we could use to test out some of these different theories that we had thought up. We tested this vehicle in a couple of different terramechanics experiments. And after that, we are still working on making simulations for this vehicle so that we can approximate its performance in a variety of different manners outside of the lab. In addition, we sought to tackle some of the robot-specific questions like path planning that would be influenced by the reconfigurability. And finally, something that we're hoping to do is to look at this in a little bit of a bigger scale, see some of the effects of scalability, sensitivity analysis to make sure that we understand how our metrics should be used in different sized vehicles. So the first thing we did was look at a variety of different robot journals over the past 40 years, and in addition to a couple conferences, and examine all of the uses of the word reconfigurable or reconfigurability. And in all, we looked at about 239 papers. This was excluding examples where reconfigurable was just in, for example, the author bio, or it was used in a completely different manner than we're talking about here. And we saw a variety of different applications that this term was used in, mostly ground vehicles and manipulation, but in addition, control, some of the software aspects, and assistive robots as well. We also noticed that there was a wide variety of manners in which the word reconfigurable was used. About 30% of these resources assumed that reconfigurable meant that the robot itself could change itself, transform itself. And in about 30% of the cases, the authors assumed that reconfigurable meant that there was going to be an outside entity that was changing the robot. And then about 40% of the time, there was a distinction made between a vehicle that could reconfigure itself and a vehicle that could be reconfigured by an outside entity. So from here, we distilled our definitions. So static versatility is something that doesn't need to be changed in any manner, but can still offer different benefits. For example, like a spork, it can serve as multiple purposes, but doesn't need to be reoriented, doesn't need to be added to or anything like that. Then manual reconfigurability would be something that's modular, that you can manually take out via the scientist or the operator and then replace with another component or reorient or put in a different component. And then self-reconfigurability would be the same idea of changing its shape, changing components, changing the manner in which it connects to another thing, but that the robot does it itself. So after we came up with our definitions, we sought to create some metrics for each mobility, complexity, and reconfigurability. For reconfigurability, as I mentioned before, we're just capturing costs here that wouldn't be present in a non-reconfigurable vehicle. And we're not including anything like weight that would be apparent in some of the other equations. For example, this would affect mobility. So these are only elements like the time it takes to reconfigure, the amount of additional components it takes to reconfigure, and the additional monetary cost of the reconfigurability that would not be present in a non-reconfigurable vehicle. To combine all of these, we used weighting constants, which are denoted as C, and summed up each of those three variables that I mentioned previously to come up with one reconfigurability cost. And this cost doesn't have any units associated with it, and each of those constants can be tweaked depending on the application. So for example, in a lab setting, it might not matter how long it takes me to reconfigure a vehicle. But for example, in a battlefield, it might be essential that I be able to complete that reconfigurability as quickly as possible. And so that weighting constant may be extremely high for the time in that scenario. We also sought to create a metric for mobility, which I'm sure everyone on this call is aware of how difficult and complex that can be rather quickly. So we sought to create an element for the area that is reachable by the vehicle, how fast it can roll over each element of that achievable area, and then how much drawbar pull it has at each section of that area. So hopefully, again, the scientists using these metrics could change these weighting constants based on whether it's important that it be able to drag things, whether it's important that it be able to travel quickly, or if it's just important that it be able to reach the majority of the terrain in question. And each of these entities could be solved for analytically, empirically, or through simulation in terms of the achievable area, the speed made good, or the drawbar pull at each of those distinct locations. We used the data set from the NGNRMM data for our examples for this, but any terrain could be used as long as it's kept consistent throughout. And then for complexity, we combined a couple of different metrics commonly used in unmanned vehicles. So here we have different values for the number of actuators, the number of linkages, the length of each linkage, and then the number of degrees of freedom. And again, weighting constants so that the scientists could value which of those elements is most important. For example, controllability may be extremely important for this vehicle, in which case the longer linkages may be very difficult to control compared to a variety of small length linkages. So after we came up with our definitions and metrics, we decided to create our own modular vehicle so that we could test out some of our theory that we came up with. I'll go through this a little bit quickly, as some of you may have recently seen some of this work presented at the recent ISTVS conference. So in creating our vehicle, we sought to create as many different modularities as possible, trying to capture many different elements of the equations that we're familiar with. So sprocket diameter, track length, track width, and track tension were eventually chosen as the 4 elements that we wanted to be able to reconfigure. For our overall design, design choices were made so that we could maximize the available elements for each of these reconfigurabilities, in addition to making it easy to manufacture. So the chassis was all made of aluminum, and we had multiple attachment points for the sprocket so that we could achieve different track lengths. The idle sprocket were each comprised of different mounting brackets so that they could have the same ride height despite difference in diameter. The driven sprocket was made in a very similar manner to the idle sprockets, but this was attached to the motor using 90-degree bevel gears so that we keep it a little bit more compact. And the track tensions, we wanted to be able to make sure they could achieve a variety of different track tensions while also decoupling them from any of the moving elements. These are a couple images in our design progression. On the top left, you can see one of our first designs using that aluminum chassis that we discussed and aluminum tubing for the supports for the tracks. And throughout this progression, we tried to make sure that we had maximize the track wrap angle around the driven sprocket, in addition to decoupling the motors from any of the reconfigurable elements so that the gear ratio would remain the same across all of the different elements. Just to show how we're achieving the modularity in each element, for track diameter, as I mentioned before, there are different track mounts for each idle. There are different, sprocket mounts for each size sprocket. So on the image on the left, you can see the longest track mounts with the smallest sprockets. And the image on the right, you can see the shortest track mounts with the largest sprockets. And these two have the exact same ride height. For track length, we're utilizing the holes on the side of the aluminum tubing, and these can be used to change where those idle sprocket mounts are placed in relation to one another. Track width is achieved by using these off-the-shelf tracks, which come in two widths, 2-inch and 3-inch. And track tension is used by changing the distance between the idle roller and the support for the spring that supports the idle roller. The closer these are together, the higher the tension on the track. We can also swap out the spring if we need a different variety, a different range of track tensions. The electrical design is very simple. This robot doesn't have a whole lot of algorithmic power built in. The path planning and everything is more in the simulation side for this robot. And so any data logging is done on a laptop that we have tethered to the vehicle. And the vehicle on board only has motor encoders, a central accelerometer, and a ground speed encoder that's on a fifth wheel to measure the real traveled speed. In terms of fabrication, we wanted to make sure we could do everything rather quickly in-house. So most components were water jet, most planar components were water jet, and the tube components were manually milled. There are a couple components that needed to be laser cut or 3D printed, and these were primarily for mounting the electrical components or shrouding the gear assemblies. So in terms of testing this vehicle, we had a variety of terramechanics experiments. They'll probably be fairly simplistic for this audience, but we'll go through them quickly. For maximum sinkage, we prepared the soil by tilling it, leveling it, and then compacting it, and then slowly lowering the vehicle on a series of times, and then measuring the maximum sinkage for each example. The results for track width and track spread fairly followed the Becker's equations for maximum sinkage for a tracked vehicle. And then for track tension and sprocket diameter, these are elements that aren't in those equations. And we noticed a slight variation for both track tension and sprocket diameter for the maximum sinkage, which was a pretty interesting thing to see. For example, for the track tension, the higher track tension had a slightly lower sinkage, perhaps pointing out that maybe the vehicle was better able to distribute its weight over the length of the track. And then for sprocket diameter, the larger sprocket had a slightly lower maximum sinkage, again, perhaps illustrating that it could slightly spread out its weight over its longer sprocket diameter. We examined the maximum pressure on fairly hard terrain and didn't see much variation across any of the 4 variables. We used a TechScan Compromat 5330, And we expect that we didn't see much variation, one, because we're using a hard terrain, so some of the benefits of these different tracks may not have been realized because it wasn't something like sand or snow. And then in addition, the pressure sensor that we were using was fairly low fidelity, so some of these small changes may not have been realized because of the size of our vehicle compared to the sensing precision of this device. For maximum traversable slope, we again used a hard terrain put with sandpaper on top of it for added friction. And we saw the greatest impact on maximum slope that we could climb was for the track length change. So the longer the track length, the higher the slope that we were able to surmount. We expect that some of these results would be very different if we were doing this on soft ground or snow instead of something like hard ground. In those examples, it may be beneficial to dig into the ground, or it might be more impactful to have a wider track for more flotation, depending on the different applications. So the next thing after we did some of our experimental results was to see if we could replicate these in simulation and see what some of those differences were between simulation and actual in the experimental cases. One thing that we are currently working on is putting our vehicle into a multi-body physics simulator and seeing if we can get similar results or if these are changed results in simulation compared to our maximum slope results that we got in practice. In addition, especially from the robotics perspective, we looked at the influence on minimum path length for each of these different variables. So for this case, we used MATLAB and we used the A-star algorithm, which, just as a review, A-star is a very common path planning algorithm. This algorithm is guaranteed to find you a path if one exists, and that path is guaranteed to be the shortest as long as your heuristic is consistent. We also chose it because it's fairly easy to implement, and we had a good heuristic here, which was Euclidean distance to the goal, which for this project is very easy to calculate and is also relevant to what we're working on. So just as a review for A-star, the algorithm expands a node if its cost to the node plus the heuristic cost, which is a proxy for the cost to the goal, is less than that of all the other nodes. And it does so successively. So for example, in this very basic case, the algorithm would choose the purple node from the start because that cost would be 4 plus the heuristic cost of 2, which is less than the blue node, which would have a cost of 3 plus the heuristic cost of 4. And then from there, the algorithm would expand the end node, and so the bottom path would be chosen. And this is a fairly easy case. There's no slopes. But as you can see here, for example, the blue line represents the path that we're going so far. The vehicle would not be able to go straight through that simulated mountain, so it would have to travel around it, and A-star would be able to find those paths. The only thing that we added here was, depending on the maximum slope that the vehicle in whatever configuration we set could travel, that would affect which nodes were possible for the algorithm to select. So in this case, the black line represents a vehicle with a low maximum slope, and the red line represents a high slope that vehicle is able to go over. So with the black line, with a vehicle with a lower maximum slope, would have to travel all the way around that mountain, whereas a vehicle that is able to surmount something much steeper could go straight through that little slope portion shown in red. So for our example, we used the maximum slopes that we found experimentally to see the path length for each of the different maximum slopes and for each that represented each of the different configurations for our robot. So starting out with the lowest maximum slope that we found, which is 38 degrees, we calculated the slope, and then for each 40, 42, 44, 46, and 48, we found how much quicker we could get to the goal, how much less path we would have to take, and those are what's shown in the table there. So for example, the yellow line would represent the shortest of the 6 paths that we calculated, and you can see that it was able to go up some steeper terrain whereas the green and magenta paths had to switch back a little bit because they weren't able to go up as steep of a terrain. So thinking towards the future, we developed a series of 3 metrics, but we still need some way to be able to value these metrics cohesively together. So that's what we're working on in the future here. This is just showing different depictions in 3 dimensions of our reconfigurability cost, complexity cost, and mobility cost, but it's somewhat difficult to value these 3 different variables and determine which one would be the most optimal solution. So we have a couple of different options here. The individual comparison, like shown in the previous slide, just comparing one variable at a time, and perhaps for different situations, it may be very apparent which variable is most important. Another way that we can compare these 3 metrics is using an aggregated analysis. So this is shown in the table here. We first normalized each of the different metrics relative to one another, and then we simply sum them, multiplied by our gain, which would be how much we value each one. For this example, we are valuing our mobility highest at 0.7, our complexity next at 0.2, and then our reconfigurability least at 0.1. And then we can view the aggregated value in the column on the right to see which of these has the best cohesive score across all 3. In addition, we're looking at doing some more complicated goal programming so that we could hopefully optimize for these 3 variables. And instead of choosing 3 different platforms, we could direct our design towards what we needed to design for and select different things like, for example, track width, track length, that would be optimal for our situation and how much those would need to vary to be able to get to the optimal solution. This slide just documents some of the work that I'm hoping to do in the coming months. So I'm hoping to find some way of integrating speed into the path planning work that I'm working on. In addition, I'm going to continue some of the simulation to make sure that I get my repeatability down in different terrains, in different areas. And then I'm hoping to add a little bit of analysis in specifically ground vehicles to what I've researched with robots and reconfigurability to make sure that that's a consistent term usage across just ground vehicles and not just robotics. In addition, I'm hoping to add an analysis on complexity to what I've already got to make sure that the metrics that I'm proposing are in alignment with what is already existing. There's a great deal of work that we have yet to do with the physics-based simulation to hopefully be able to approximate vehicle performance without needing to do some of these experimental testings or relying on some of these analytical or empirical equations that were developed for different scale robots. And finally, we're hoping to examine some of these big picture issues like scalability, sensitivity analysis, and then, as I mentioned, optimization to hopefully make some of this work as easy to use and helpful as possible. So in conclusion, the primary objective of my work is to create a quantifiable system for estimating the mobility, complexity, and reconfigurability of an unmanned tracked vehicle so that a designer could optimize these for the best possible performance that they could with this vehicle. Some of the other things that I'm working on are formalized definitions for all of these different entities and thinking of reconfigurability as a concept instead of just an afterthought. In addition, our vehicle that we worked on and tested is a contribution that we're hoping can provide a little bit of light into designing something for reconfigurability instead of just, for example, designing for performance or for manufacturability. In addition, we hope that the comparison of our work from simulation to equations will be able to shed some light into the realm of small tracked vehicles to hopefully be applicable for other terramechanics researchers. My research would not be possible without the people listed here, and I thank them, in addition to everyone that helped out to enable me to talk to you today. And I appreciate Jenna, Mohit, and everyone at the ISTVS seminar series for helping me put this on. So with that, I will hop over to Hopin and see if we have any questions.
Hi, Hannah. Yes, we do have a couple of questions. So I think I'll just go ahead and read them out first before actually inviting people to ask questions directly. So, firstly, by Jenna had a question. Hi, Hannah. Can you speak a bit about your origin story, how you came to work on small unmanned vehicles, and similarly, where would you like to take this work in the next, say, 2 to 6 years?
Sure. Thanks, Jenna, for the question. So I got into the area of reconfigurable ground robots through my master's work. I had the fortune of helping out with the National Robotics Engineering Center, or NREC, in Pittsburgh. They were working on a next generation ground vehicle with a wheel that could transform into a track. And I presented that at Prague in 2019, some of the early prototypes. But if you check out YouTube, there's some more impressive later prototypes. But that really got me thinking about the whole idea of reconfigurability. It was my background's in mechanical engineering and robotics. So this idea of innovations in mechanisms is really interesting to me. A lot of robotics, is more on the machine learning and AI side of the house, as opposed to, my interests, which is mechanical. So this idea of creating innovations on the mechanism side is something that's really interesting to me. So that's how I got started in reconfigurable ground robots and small vehicles, mostly for the ease of accessibility, something that I could, create in 1 year. We thought small vehicles would be a little bit easier. In addition, a lot of the ground vehicles that we've seen, for example, like EOD or bomb disposal or urban search and rescue, are more on the smaller scale. So that's really where we took interest in the small side of things. And then where I would like to take the work in 2 to 4 to 6 years is it would be awesome if the dream would be to create a program that the researcher could say, okay, I'm interested in this type of terrain, in this type of slopes, this type of sand, et cetera, et cetera. I'm interested in this type of terrain. My payloads are expected to be this amount of kilograms, and I need to be able to get there as fast as possible. Hit enter, and then a series of parameters pops up that's saying these would be your optimal ranges for your width. This would be your optimal ranges for your length, and so the designer could inform their vehicle design based on these parameters. I hope that answers your question, Jenna. Thank you for asking.
Thank you, Hannah. I would like to invite Dr. Alex Keane and Mr. Lines as they are posting questions in Q&A. If you could please click on the blue share audio and video button, we could have a live conversation about your question.
Oh. Hello, Moet. Can you hear me?
Yes, we can hear you.
All right. Okay. Thank you. Well, do you want me to ask a question, or do you want to go to someone else first?
No, you could go ahead, please.
Okay. Well, the first one, I was thinking, well, you were describing different sorts of robots. Have you got any examples, a little bit like Transformers, but in a sensible industrial context? Any examples of drones that will convert into terrain robots? It sounds to be quite useful that you'd be able to, applications, for example, search and rescue, and particularly in ag come to mind, fast transport, and then energy efficient work.
Definitely. So the first one that comes to mind, and I'd have to do a little bit more research to see if there's more examples, but in the DARPA Subterranean Challenge, I believe that one of the teams did create a drone that could transform into a wheeled vehicle. So it was a very, very lightweight vehicle. As you can imagine, for anything flying, they would need to be pretty lightweight. But that was, I think, an extremely awesome example of dramatic reconfigurability, right? From something that can fly to something that can roll. And that was exciting to see. And I wonder if in the future it could be used for, more robust applications.
Okay, I mean, I can think of lots. I mean, just one example in agriculture now with the sort of development of precision agriculture, rather than spraying a whole crop for a bit of disease in certain parts, you might actually go to the small area where there is a problem, may even be, for example, a fruit tree. If you're using a drone, the effect of the draft is going to send any chemicals you use in lots of different directions. But if you can land and then actually move into the right position with a trained robot, you could actually remove the disease mechanically, or possibly even spray, but hopefully mechanically, or even spray or do the work with a lot more precision than if you were trying to control a drone hovering. So, and obviously in search and rescue, then as soon as you find people, get onto the ground and actually get close, maybe do something useful.
Definitely. I think those are both great applications. And maybe I know one of the professors, Ramon, in the ISTVS works a lot with agriculture, and agricultural robots, and he might have explored this. I'm not entirely sure. I don't have too much experience with agricultural robots, but I can see both agricultural and search and rescue as great prime examples for when you need to be able to traverse really far very quickly, but then also get on the ground and do some actual work on the ground.
Yeah, a little bit linked to that, really. It's almost a slightly follow-up. Have you tried to link reconfigurability to any different sort of applications? Not worrying about the drone thing, but for example, examples might be ground sampling in geotechnics, or obviously the search and rescue, or another one, which I know that some of my old colleagues from years ago were looking at, which is herding animals. Rather than using dogs or people, things like geese even, which are not the easiest things to herd. Have you sort of, or is anybody actually trying to look at what sort of configurations would actually work for different applications?
I'm not too sure, especially the herding example is something I'd never thought of until, 3 seconds ago when you mentioned it. That's a pretty interesting example. But I think this idea of you have a problem, and now what configuration, because we've seen, that 4-wheeled vehicles, 6-wheeled vehicles, drones, that these are all so different from one another. And once you choose a path, going down that design process is a rather linear one, where designing a drone would be completely different from designing a 2-wheeled tracked vehicle. And I don't know of any research right now that can, for a given application, tell you what the optimal platform is. But I'm hoping this work does at least one little slice of that equation.
Okay, right. I'm just sort of thinking there. In the UK, there's lots of examples of sheepdogs which may actually be worth tens of thousands of dollars. So a really good sheepdog could be worth $20,000, $30,000, $40,000 even to the right person. It may take quite a long time to train. So robots that could do the work, I'm sure, would be a lot cheaper, and they wouldn't take quite so long to train.
Yeah, that's a very fun example, and I'm sure that there's a lot of safety concerns that would need to be taken into account with anything with animals, but I'm sure they could be overcome.
A challenge.
Yes, definitely.
Yeah. Okay, thank you.
Thank you. Those are fun things to think about.
Moet, you're back on again.
Thank you, Dr. Keane. Mr. Austin Lines has a couple of questions. If you would like to join the conversation. Yep.
Hi. Thank you for your talk. Just a clarifying question: is the rover that you designed static or manually reconfigurable, or it's not like self in any way? Yes,
it is, and we did some work with designing, but we didn't implement any of our automatically reconfigurable ideas into this robot. But the work I did with my master's is an example of a automatically reconfigurable vehicle. But yeah, we didn't go down that path, but it's definitely something that we are interested in.
Got it. And then my second question was, have you thought about the energy efficiency and using that in your metrics?
Thought about, but have not implemented in any way. I think it's an interesting, definitely interesting. And I think we tried to kind of use speed made good and drawbar pull as almost proxies for energy. But I think energy is ultimately, one of the most helpful things. And if you have any resources about, some of those methods for approximating that, I would be all ears for those examples. But no, we didn't incorporate any. We have thought about it though.
Yeah, I just know that deciding between tracks or wheels is a big decision that needs to happen pretty early on in the design process. So, and I guess, was your master's work with the wheel that could reconfigure to the mat
Yes,
track
sir.
sort of
Yes, sir.
situation? Got it. Cool. All right. Thank you.
Thank you for your questions.
Yeah. So, if anyone else among our attendees today would like to join the conversation and ask questions, we would like to have you here.
So it looks like someone asked about the 2019 conference. If there's, I can
Oh,
speak
yeah,
on that briefly.
Yeah, I didn't read it out earlier, but yeah, that was one question.
And I mean, you can also jump in since you were there too, Mohit.
Yeah.
I had a blast, and I think this question probably brought it up because Mohit mentioned I got a very nice grant that Professor Ayers helped facilitate that helped pay my way there. So I didn't have a lot of funding from my university for this experience. So the travel grant was super helpful. I was able to, I believe, pay for all of my flights with that grant. And the conference itself was tremendous. The 2020 that got moved to 2021 conference was super fun, and it was great to hear from everyone. But seeing everyone in person, it was my first experience with ISTVS, really, and everyone was just the thing that was most amazing. I mean, it was super fun to explore Prague, super fun to hear about all of the the keynote speakers. There was even a student seminar or student session where we learned more of a classroom style, but more informal, where we learned some techniques, skills, tools that we could use. But the thing that I was most surprised about, in a good way, was that everyone is just super approachable. Like, I've read so many papers from, and then you would meet the person that you've read their paper, and they were just like, how can we help you? Like, what are you working on? They were super interested in what we were working on and how we could facilitate it. And we just had tons of conversations with them. Mohit's advisor pretty much took me under her wing, and we, it was just a super approachable, kind environment that I learned a ton from. So that was my experience with the 2019 conference. Mohit, is there anything I missed with that?
Oh, no. I just would have added some names, but I've had pretty much the same experience. It was the first conference I've ever attended. And yeah, it was fun. The first day we just went around roaming, and then there was this professional course. I still remember, on the first day, it was towards the end, just after the lunch, the second session was about to start of the professional course, and behind me, Dr. Sally Shuk was sitting, and I was just sitting in a corner reading through the notes and slides and everything, and she randomly says, "Hi, I'm Sally," and I was like, "Okay, I've read your paper." That was my first reaction. But yeah, it was fun. You summarized everything that I wanted to say. So yes, if we do not have any more questions, I think we'll move towards closing for today's session. So firstly, thank you, Hannah, for telling us about your work and making us think more about it. We will soon be publishing this to YouTube, and we'll send you a link as well. So for everyone, we are currently working more on the ISTVS resource initiative, which is headed by Dr. Alex Keene, and we are inviting graduate students to contribute more to the resource initiative, which we are trying to create as a place where people can get to learn more about what aspects of a specific kind of terra mechanics sub branch that you should know more about, and who are the like people or the books, kind of books or journals that you should follow. Further, the ISTVS currently is also undergoing its annual membership drive, and if interested, we would like to invite everyone to join the ISTVS membership drive. Join the ISTVS by applying for membership through these links. So, and lastly, this is the last seminar of the ISTV's digital event series for 2021. The next set of seminars will start from January, and everyone will surely get an email from ISTVS through Newswire. Also, because Hannah, you mentioned about it, Professor Paul Ayers will be presenting in this series on 9th February 2022. That would be an interesting conversation. That would be an interesting seminar for you to attend to. So, everyone, thank you for attending today, and have a great day, evening, night, depending on where you are.